Hi everyone, welcome back. Today we're going to talk about shape memory alloys and their unique behavior and what makes them different from normal alloys. So we are using shape memory alloys in Mars rovers and robots that are going to space. We are also using shape memory alloys in biomedical engineering, as the image on the right, using stents to open up arteries using shape memory effect of these special alloys. So what does shape memory mean? Shape memory alloys. Shape memory alloys are alloys who can recover their deformation back to their original state. What it means that if you bend a metal with a normal alloy, if you bend a alloy bar, and if you heat it up or you trigger it in some other way, you won't be able to recover the deformation back. It won't go back to its original shape. But when you have a shape memory alloy, when it's bent like that, for example, if you heat it up, then it will by itself go back to its original shape. So in some ways, it's remembering its original shape. And for example, when you heat it up, it would just go back to its original shape by itself. And that's something that a normal alloy cannot do. Imagine you are just bending a bar made of aluminium, and if you heat it up, well, nothing happens to it. At least it won't go back to its original shape. So that's the main difference of shape memory alloys and normal alloys, and that's the ability to recover its plastic deformation with some external trigger that could be heat or something else that. And by that, I mean when you heat it up, for example, a car that is crashed and you have all these huge plastic deformations on the trunk of the car and the body, and imagine you're heating it up and it's able to recover back to its original state like nothing happened to it. So we want to take a look at the structure of shape memory alloys and also later on take a look at the stress strain curve of shape memory alloys to see to be able to see their behavior with respect to their crystal structure and also stress strain behaviors, and how would it look like on those curves when we are dealing with shape memory alloys. So shape memory alloys, basically they have two distinct structures at high temperature and at low temperature. So and those we call austenite in here and martensite in here. So austenite for shape memory alloys that apply to most of them is a high temperature structure that we call austenite, and low temperature structure we call martensite. So these two structures that are here, two martensite, these are low temperature variation of shape memory alloys, and austenite is a high temperature structure. If you heat your shape memory up, and depending on type of shape memory alloy that you have, these temperatures could vary. Even with one type, we could alter these transition temperatures. But imagine you have two distinct ones, and above that, you get austenite, and at the lower temperature, you get martensite, and you get this phase transition into different crystal structures when you by heating up and cooling it down, that we call austenite and martensite. So that's the basic concept of it, that when you have a martensite, when you heat it up, it goes to austenite, you cool it down, it goes to martensite again. So how does it look like when you are dealing with stress strain curve? What is a stress strain curve of shape memory alloys? And that's what you see here. So this stress strain curve, all of it together, um, it contains shape memory effect and also superelasticity or pseudoelasticity effect of these special alloys. So let's make sense out of this stress strain curve together. So that's the main part of discussing shape memory alloys, because general information about shape memory alloys you can find online everywhere. But this is about understanding stress strain curves of shape memory alloys and relate them to their structure, either martensite or austenite. Okay, so we will focus on this. So let's look at the stress strain curve. On the slide, you will see that if we now we want to focus on one part of it, and that's the part. So we want to focus on this stress and this strain curve. So we are here. When we are discussing here, just like a normal alloy, you start with deformation and then you enter the elastic deformation region, which is the linear line here, until somewhere around this point, and this point is our yield point, that after that we begin with plastic deformation, just like a normal alloy, and you get some strain hardening as you apply deformation, and this is our strain. So we are going this way. When you project it down to the strain, you are applying deformation and you get strain hardening because your material is getting hardened. And if you're unfamiliar with this concept, watch the previous videos. You need those about plastic deformations and alloys to be able to follow on this. But we move on. So as you're applying deformation, it becomes stronger, stronger, and stronger because of strain hardening, and then you end up at point B, okay? So because now we are at low temperature, dealing somehow with a normal alloy, um, here at low temperature, for a shape memory alloy, we are at martensite phase, right? So at B, we have martensite because it's low temperature. We assume it's low temperature. And also at A, where we started, we also have martensite, two types of martensite, okay? The only difference between two martensite is that one martensite has no strain on it. When you're at point A, there is no strain on your martensite lattice. But when you go up this blue line and you apply deformation, your martensite will be strained. That's the only difference of these two martensite. So now we applied some deformation. It experienced some strain hardening. So it's plastic deformation. We ended up at point B. Now we want to unload. So when you want to unload, you go down this blue line, right? You go down this blue line and you're unloading just like a normal alloy. You go down parallel to your elastic line. So that was your linear elastic line. And when you're unloading, you go down parallel to that line. So you end up at point C when you unload. And we have some strain, again, just like a normal alloy remaining in your material. So this is the amount of strain from A to C. From A to C is the amount of strain that has remained in your material as permanent plastic deformation, just like a normal alloy. Now the difference comes here. So if it's just a normal alloy, if you heat it up, you cannot recover this strain. You cannot recover that when you heat it up, if it's a normal alloy. But for a shape memory alloy, now we want to heat it up. Along which axis? So this axis that I'm marking, that is marked at T, this axis is temperature axis, okay? Now we want to increase the temperature. So from point C, we increase the temperature, this red line. We are increasing the temperature, and as you are increasing, you're going up this line, the temperature line, and also you are, if you project it to the strain line, you will see that if I can erase that, yeah. So when you are going up this line in this direction, you are heating up. And as you are heating up, of course, you are going up this line, which is temperature. And also, when you project it to the strain axis, it also shows you that on the strain, you're going this way on the strain axis. What it means that you are recovering the plastic strain of your material as you are heating it up. So when the recovery becomes complete, when you completely go from playing games with me again, so when you are going from point C to point A, then you have fully recovered your strain. That will happen when you heat up at point O, somewhere between AF, a point D, and point O. So this is when you are here, and when you project it down to strain, you will end up at point A. It means that you have fully recovered your strain when you are heating it up anywhere above point AF. That when you project it, it goes down to point A here, which means that you have fully recovered. So that's the shape memory effect, or thermal shape memory, because we are making our material to remember its original shape at a high temperature. So again, you start from point A, you apply plastic deformation until here, you unload, you come back down, and then you start to heat it up. And as you heat it up, you recover your strain. Something about these points that we are having here, you can see AF and AS. They are abbreviations for austenite start and austenite finish, the high temperature phase. So this is where you begin with formation of high temperature austenite, and AF is where you finished with forming all the austenite phase. So whatever that is forming after AF, you have 100% austenite phase. And between AS and to AF, you still have some transitions remaining from martensite to austenite, okay? So your recovery starts from AS and finishes at AF. So after AF, you have 100% austenite, and means that you fully recovered your material. Now, what you can do here is to cool down again along the temperature line. And then if you cool down from austenite, you go back to martensite again, and the whole story can repeat itself while you are deforming and then heating up to recover. But when you are at point O in here, which is a high temperature austenite, we are above AF. So with respect to temperature, so we have everything austenite. When you are now start deforming at austenite phase, as you can see on this stress strain curve, so this is your loading. You are loading along this line. You are loading like that up to point E. And then when you unload, it's not like point B. Because you are already at high temperature austenite phase, at point E, when you start unloading, it unloads like that. So it fully recovers by itself down to point O again. So you load and you unload, and you directly go back to your original shape when it was unloaded, and that's because you are above AF, you are at high temperature austenite phase, and it recovers by itself. That property that you apply plastic deformation, it's a lot of deformation on a material, on a shape memory alloy, and it recovers by itself at the same temperature, we call pseudoelasticity or superelasticity, because that's kind of like elastic behavior, right? Elastic behavior is reversible behavior, just like this flat line here that we have. But this is pseudoelastic behavior because it doesn't come down along the same line. When you apply the plastic deformation, there's an area in between. So it's not exactly coming back along the same line. The pathway is different, but anyway, you can recover all the deformation that you apply. And plastic deformation can be much more than elastic deformation. So when you will do it above AF and you are applying like that, if you let go, just like a spring, it will go back by itself. So that's a difference between shape memory effect and a pseudo elasticity.